I'll start recording. So thank you everybody for getting your exams into me. I haven't started going through them yet, but I will start going through them soon. I do want to remind you that you are allowed to redo the problems that you get wrong. Oh, hold on just a second. All right, sorry about that. You will be able to fix the problems you get wrong. So on the exam, I'm going to mark the problems you got wrong, kind of circle where the mistakes happen, or at least the first place where the mistake happens, and allow you a chance to resubmit to get some credit back. Let me just double check what I decided on my syllabus because this is the first time I've ever done something like this before. So you can get back up to 50% of the points that you missed. And you'll have a week after I finish grading. So after I finish grading, I will send out an announcement that says, hey, all your tests have been graded. You can go look at them and see what I marked wrong. And then you can take those problems, redo them, hopefully find your errors, and resubmit them and get up to 50% of those points back. So just so you know, whatever grade you get on this one isn't your final grade. You still have that opportunity to get more points back. I'm trying to make this semester as I want you to learn calculus, but I want everything to not be super high stakes. I want you to know that there's opportunity to come back from bad grades. There's opportunity to show me that you've learned. I don't think that education necessarily needs to be that you get it right on the first try. So I want everyone to have the opportunity to get the grade that they want in this class. If you feel like your homework scores have been a little bit low, hopefully these homeworks going forward will be better, but I'm even up for offering more opportunities to make up homework assignments. We'll just kind of see how things go going forward. But I want everyone to know that that your grade is never set in stone. I am willing to give you opportunities to show me that you know more than what your grade maybe says. Okay. So beyond that, we had not finished 2.2 yet. So we went to go talk about velocity, but we hadn't talked about it in section 2.1 because I skipped it because I was like, well, we're going to talk about this later. So I'm going to go back to section 2.1. This is page 50 in the notes. As a note, I did I re-uploaded section 2. It now has the answers to the unit 2 exercises. So I thought I was going to upload the answers in a separate document, but I just re-uploaded the Unit 2 notes. So you can find the answers to all the exercises in Unit 2 now in the Unit 2 notes, just so you know. All right. Erasing this because we are coming back right now. So this is from Unit 2.1, page 50. It's the page that looks like this at the very bottom of it. So we're going to talk about real-life representations of the derivative. And the one in calculus we talk about a lot is velocity. So in real life, the derivative represents the instantaneous rate of change. So for example, and I did talk about this at one point when we were first talking about the derivative, as opposed to getting the average speed of a car during a road trip, the derivative, the instantaneous rate of change, would be the exact speed of a car at a given time. So whatever your speedometer is telling you. So instantaneous rate of change is how fast is an object going at a particular moment. Not overall, not on average, but just at a particular moment. So we have some notation that we use. For position of a function, the position function, we usually use the function s of t. All right, so s of t is the position function. And this can mean different things depending on what you're talking about. Sometimes position refers to height, sometimes position refers to distance. It all depends on the context of the problem you're working in. And if you take the derivative of the position function, the derivative of the position function gives us the velocity function. It gives us the velocity of the object. And for the velocity function, so unlike the position function where you're like, well, s, it doesn't, like, why would s represent position? Why isn't it p of t? Because mathematicians said so. There's probably a better reason than because mathematicians said so. But for velocity, we actually use v of t. So what you'd hope it would be. So if you take the derivative of the position function, this gives you your velocity function. This is really, really important. You know, maybe put some like something to make it really stand out in your notes. And I'll say it one more time down here. The derivative of the position function is the velocity function. All right, this ends up going deeper. You end up getting another level of this a little bit later on where we talk about acceleration. But for right now, if you have a position function that tells you the position of an object, so maybe your position function represents like how far a car has gone from when it started moving to when it stopped moving. If you have that function that tells you where that position is at any time, if you take the derivative of that function, the position function, that tells you the velocity function, which will tell you how fast at any given time that object was going. Can I answer any questions, concerns, comments? Maybe I'll use this time to say that I think I was in a Spanish class. I think it was a Spanish class in my undergrad. And the instructor, his thing was always, are there any questions, comments, or sports scores? And I mean, this was a long time ago, guys. We're talking, this is like 10 plus years ago. And I still, when I say, are there any comments or questions, I have to stop myself from saying sports scores. So there's your fun anecdote for the day. I don't know why. I don't know why that was what he said, but that was always what he said. And it stuck with me. All right. So I'm going to go ahead and go back to this page here. This is back in section 2.2. So this is page 60 in 2.2. Now, when you get the new notes, these pages are going to be slightly different. So if you download the new notes, the pages will kind of be off because the answers took up, well, no, the answers are at the end of the section, so it won't take up pages. So the pages will still be right. All right. So one more time on this page, I'm going to make a note that velocity is the derivative of the position function. All right, I'm just going to make a note of it right there. All right. And so the position function measures the distance between the object and its starting point. So what's kind of important, if you're measuring the distance between the object and its starting point, you can end up having negative position. Because imagine if you like start right here, if this is your starting point, you know, you can go this way, but then you can like turn around and go this way. And then you can like go this way. And you could end up right where you started. And your position would be 0 because you hadn't moved at all from where you started. So the positions function talks about starting at a certain point and the distance from that point at the end. Now there's another function called the distance function that actually measures the actual distance you traveled. So it would take this distance and add it to this distance and add it to this distance. And that's called the distance function. And we'll talk about that eventually, but we're not going to talk about that right this second. But the position function measures the distance between the object and its starting point. And that means that because velocity is measuring the instantaneous rate of change, velocity can be negative because if you're going in the opposite direction, so you'd have positive velocity going this way, but then you'd have negative velocity going the opposite direction. So position and velocity can end up being negative. But oftentimes we're talking about going forward, but it can be negative. There are plenty of opportunities for it to be negative. So let's talk about an object. Position of an object is given by the function s of t equals 1/4 t to the 4th plus t cubed minus 8t squared minus 48t, where s is measured in feet and t is measured in seconds. And I also want to point out here that I am somebody who gave up on physics. I went into my undergrad thinking that I was going to be an engineer, and then I hated physics, and then I didn't do physics after I hated it. So if I say something that's not correct in physics terms, just forgive me. I know the math side of things, but the physicsy side of things, I mean, I got schooled by a class of high schoolers once. It was quite embarrassing when they're like, your units aren't right. You're not using the right units. Sorry, I don't do much in physics. I can do the math side of it. So do forgive me if you know more about physics than me, which there's a good chance you do. All right. Here we go. So we have this position function here, and we want to find the velocity of the object after 5 seconds. So what this is asking for, it wants us to find v of t, right? And then we need to plug in t equals 5 to find the velocity at 5 seconds. That'll give us v of 5, velocity after 5 seconds. Right? So our original function here, velocity, is the derivative of the position function. So remember back to how derivatives work with our power rule. We take the exponent down and we're multiplying it by the number in front. So 4 times 1/4 is 1. So I'm not going to write anything there. I'm just going to write a t because we don't write the 1 in front of the t. And then 4 minus 1 is 3. All right, so remember, power rule says you take the exponent down, multiply it with whatever number is in front, and then lower the exponent by 1. This works with polynomials. For the next one, 3, bring it down in front, and then we lower the exponent by 1, so it's t squared, minus 2 times 8 is 16. And then 2 minus 1 would be 1 for the exponent, but I'm not going to write the 1 there because we don't write 1s for exponents. And then remember, for the minus 48t, if there's no power on the variable, it just disappears. So it becomes minus 48. The long way to write this out, just in case you want the long way in your notes, would look like this. So essentially, this 4 and this 1/4 become a 1, which disappears. This 8 and this 2 become a 16, which is right here. And then there's no need to write the 1. And then t to the 0 is equal to 1. And 48 times 1 is 48. Just to make clear the math that's going on there. So we have this function now, and we can plug in 5 seconds to the function to find the velocity after 5 seconds. So we're plugging in 5 for t. So we have 5 cubed plus 3 times 5 squared minus 16 times 5 minus 48. And I believe this comes out to 72. And we'll put units on it in a sec, but let me just double check that. what did I do here? Plus 3 times 25, 72, yep, 72. All right, so then units. The way that units are going to work for velocity, with the position function, the s of t function, those units are going to be stuff like feet or meters or miles or what other things, centimeters, something like that. Those are the types of units you get for position. For velocity, your units are going to be feet per minute or feet per second or meters per minute, meters per second, meters per hour. So it's going to be a distance over a time unit. So like miles per hour or feet per second or meters per minute, etc. So it's a distance over a time. So here, because our distance was measured in feet and our time was measured in seconds, our units are going to be feet per second. Can I answer any questions there? Right. So determining the time at which an object is at rest. So we have the same function here. We want to know when the object is at rest. Being at rest would mean that you're not moving. And not moving would mean that your velocity is 0. Now, what's really important, up here, we found v of 5 because this was the velocity after 5 seconds. We don't want to plug 0 into this function because v of 0 would tell us the velocity at time 0. Instead, what we're looking for is at what time, so when is v of t equal to 0? So we're going to take our velocity function, this guy right up here, and we're going to set him equal to 0. So we have t cubed plus 3t squared minus 16t minus 48 equal to 0. And we have 4 terms. Typically, the factoring method we want to use is going to be factoring by grouping. So in my first group, I can pull out a t squared, and I'm left with t plus 3. In my second group, I can pull out a negative 16, and I'll be left with t plus 3. Now they have a t plus 3 in common, and I can pull that t plus 3 out. That'll leave me with a t squared minus 16. And then we can factor t squared minus 16. So we have t plus 3 times t plus 4 times t minus 4, because it's a difference of squares. So we'll get t equals negative 3, t equals negative 4, and t equals 4. Now, I did tell you that position could be negative, that your velocity could be negative, but the one thing we don't allow to be negative is time, because essentially at time 0, that's when the object starts moving. So having negative time doesn't make any sense because at negative time, the object hadn't started moving yet, so there's no sense in keeping those. So we can't have negative time. So the only real answer that we have is this guy here. So the object is at rest after 4 seconds. Sometimes students ask me, like, do I need to like write down this whole sentence? No, but you do need to put units on your answer. So your very minimum answer would be t equals 4 seconds. That would be the minimum requirement for your answer. So you don't have to write out the full sentence, but you do need to write out at least t equals 4 seconds. You need to put the units on there. All right. It's very quiet today. Questions on velocity so far, and all? Okay. Okay. We'll just keep going then. So just a quick biology application. So in biology, it's important to monitor the population of any given species in the ecosystem, and we can use math to model populations over time. Granted, it gets a little bit more complicated than just using math to model populations, but we'll keep it simple for this class, right? We're not biologists in here. Or maybe you are, but I'm not. So this is simplified, all right? So the population of a given species was monitored from 1950 to 2000. Based on their data, the scientists created a function, P of t, which best modeled, that's spelled wrong, modeled the behavior or the population. Here, t of 0 corresponds to 1950, and t equals 50 corresponds to 2000. So essentially down here, this is the year 2000, not 2000, 1950. And this is the year 2000. And this is population. Using the graph, determine the intervals on which p prime of t is less than 0 and interpret what that means. All right, so p prime of t less than 0. Remembering that p is population, and the derivative of a function gives us the instantaneous rate of change. So this p prime of t part equals the instantaneous rate of change of the population of whatever the species is. So how much was the species, at what rate was the species changing? Was it decreasing? Was it increasing? And being less than 0 would mean that it's decreasing, right? The instantaneous rate of change is decreasing. So saying p prime of t is less than 0 is saying that the population is decreasing. So interpreting what it means, this is the interpretation of what it means. For p prime of t to be negative would mean that the population is decreasing because the instantaneous rate of change is negative. Now, where is this happening on the graph is the next question. In general, a negative derivative means the slope of the tangent line is negative. Tangent line has negative slope. So thinking about like a tangent line having a negative slope here, right? Like these are all tangent lines with negative slope. Having a negative slope for the tangent line means that the function is decreasing there, right? Because in order for that line to, I can't draw very well, in order for that tangent line to be negative, like if you have a increasing part of the graph, your tangent line will be positive, but the only places where you're going to have negative tangent lines are where the graph has just started to decrease. And I want to really emphasize this because this is an important point, not just relevant to this problem. Derivative being negative means the original function is decreasing. So if I look at my graph and look at the places where my function's decreasing, looks like I am decreasing here. And looks like I am decreasing here. So those intervals of time, and remember, time is being measured in these units past 1950, so we're not going to use these when we go to do our interval, because it does say the interval. We're not going to use these 1950 and 2000 numbers because t was being measured in these units here. But the interval on which this happens is from 0 to 10 years. And really, I'll just say and 30 to 40 years. Right? So by looking at this graph, we're able to tell that the derivative is 0 when the original graph is decreasing. The derivative is less than 0, so derivative is negative when the original graph is decreasing. And that happens between 0 and 10, and then 30 and 40. All right. Questions, concerns on section 2.2 before we finally get to section 2.3? Okay. So section 2.3, unit 2.3, product and quotient rules and higher order derivatives. So if you remember back, I don't know. Where is it? All right, back here. This is back in section 2.2, page 56. Back here I said, hey, if you have two functions that are multiplied together, you can't just take his derivative and multiply it by his derivative. I said that we get a rule for that later, and that time is now. So prior to this, when we had two functions that were being multiplied together, you did have to actually FOIL them out first and then differentiate it because we didn't have a rule. Now we're going to get rules. So this is the one that students get wrong the most because they forget about these product and quotient rules. It's really, really important that you internalize that when two things are multiplied together, that you have to use product rule. So product rule says that the derivative of two functions being multiplied together is the derivative of the first function multiplied by the second plus the derivative of the second function being multiplied by the first. In shorthand, we say f prime g plus g prime f. Now, every math teacher ever has their own different way, and different websites have their own different way of saying it. Some websites say like this in reverse. Some websites will say fg prime plus gf prime. I mean, every website does it differently. Every math teacher does it differently. But the way I'm going to say it, and the way I'm going to continue to say it, is f prime g plus g prime f. It's the derivative of the first times the second plus the derivative of the second times the first. For quotient rule, this is when you have two functions that you are dividing. So you have a function on top and a function on the bottom. The derivative of a quotient of two functions, it's very similar to this guy. All right, so it's very similar. In fact, I'm going to select it, but it's more. I'm going to take this and show you how it's similar. All right. You take this part, but then you take this plus sign. Can I move you? I just want to move you. You take this plus sign and you get rid of it and you make it into a minus sign. This is actually the shorthand, so sorry, I should probably put the shorthand down here because this is the shorthand version. Over the bottom function squared. So in longhand, f prime of x times g of x minus g prime of x times f of x all over g of x quantity squared. So f prime g minus g prime f over g squared. It's the same thing, but you change it to a minus sign and you put it over g squared. So there's a reason that I like having this order this way. So some books will put this guy first, but then when you go to do the quotient rule, it makes more sense to learn it this way because then it's in the same order when you come down here. So one thing I've heard somebody say is low D high minus high D low over low low. So I guess over low low is how I had one student tell me that they memorized it. Low D high minus high D low over low low. Because you take the low being the bottom function. So the bottom function times the derivative of the high function of the top function minus the top function times the derivative of the lower function, the bottom function, over the bottom function squared, essentially. I've had one student tell me that was how they memorized it, so I'd like to give you options. All right. So let's actually use this. Let's use these rules. So down here, with this example, we have a product of two functions. So we're going to be using product rule because we have two functions being multiplied together. And product rule is f prime g plus g prime f. So when you're first starting out, oftentimes you're going to kind of write everything out. So h of z, not h of z, h of z is this function here. Oops, pointer. This function here. Our first function, so we need to figure out which our first function is and what our second function is. So this is our first function. We're going to call this guy f, and this guy will be g. So our function f is z squared minus 3z plus 1. And our function g is z cubed minus e to the z. We're going to need the derivative of f, right? So we have like f prime, and we also need f. So we need to know the derivative of f. So taking this derivative, just the derivative of this guy, of this first one, we have 2z minus 3. Bringing the exponent down in front, lower the exponent by 1, and then with 3z, the z just disappears. And then we also need g and g prime. So g prime is going to be 3z squared. And if you remember, the derivative of e to the z, or e to the variable, is just e to the z. So the derivative of h, this original function h, once more, it's f prime g plus g prime f. And I am going to color code it for a tiny bit while we get used to it. So f prime is 2z minus 3. And then g is z cubed minus e to the z. Oops, I was going to color code it and then I literally didn't. F prime is 2z minus 3. G is z cubed minus e to the z. Plus g prime, which is 3z squared minus e to the z, times f, which was z squared minus 3z plus 1. And that's your final answer. So f prime g plus g prime f. Now, what I will make you aware of right now is that basically any cheating app, any math solving app out there is going to give you your answer in a way that looks much, much different. It's really, really easy for me to tell when an answer isn't your own, when you're giving it in a way that isn't the standard way that we'd give our answers for these problems. So I don't like pursuing academic misconduct charges. Please don't cheat. I mean, it's okay if when you're studying, you're using a math solving app to kind of help you learn to study, but it's not okay on homeworks or on exams to use these math solving apps. So just please caution you against doing that, because the answer will look much different and it will stand out and it will be very easy to catch, is why I'm saying that. All right, looking at this second function down here, instead of having a product of two functions multiplying together two functions, this one's a quotient, so it's a division of two problems. So we would want to use the quotient rule. So that's f prime g minus g prime f over g squared. Now I'm going to, for purposes of, because we use f as our baby function, I'm just going to rename him big F so that we don't get confused with baby f's. And then the top function has to be f, and the bottom function is g. So f is x squared plus 1, and g is x squared minus 1. F prime is 2x, and g prime is 2x. So our overall derivative using quotient rule, so f prime g minus g prime f over g squared. F prime is 2x. G is x squared minus 1 minus g prime is 2x, and f is x squared plus 1. And then the function g was x squared minus 1, and then we square that. And that's our final derivative. So I'm going to kind of scroll down here. I'm going to give you a few to practice before we move on to the next page. Oops, let me give it a function name. So try these derivatives out. I'm going to go ahead and put myself on mute while I do this, and then I'm going to put on a 5-minute timer once I have a few of them written down. ahead and put that timer on. I'm going to pause the recording, put a 5-minute timer on. All right, so you might not be done with all of them at this point, but hopefully you're done with maybe 1 or 2, maybe a little bit more. I'm going to start kind of going through these. And I'm going to see if I can do it by see if I can just do this by moving them around. All right. So for this first one, product rule, we have F, we have G. So F is 4x to the 5th minus 20x cubed plus 2x minus 1. His derivative is 20x to the 4th minus 60x squared plus 2. For G, he's e to the x plus 5x cubed minus 7. And the derivative of e to the x is just e to the x plus 15x squared. And the derivative of 7 is 0. So putting this all together, we're using f prime g plus g prime f. I'll color code it. So f prime was 20x to the 4th minus 60x squared plus 2. G is e to the x plus 5x cubed minus 7 plus g prime is e to the x plus 15x squared. And then f is 4x to the 5th minus 20x cubed plus 2x minus 1. So I know it looks really long, but there it is. Questions or comments on part A? Hopefully that one went okay. For part B, the numerator is f, the denominator is g. So f equals 9z to the 4th minus 7z squared plus 2z plus 12. The derivative of that is going to be 36z cubed minus 14z plus 2. And in the denominator, g is e to the z, and his derivative is e to the z. The derivative of our big function m f prime g minus g prime f all over g squared. I'll just write g squared like this. So f prime, 36z cubed minus 14z plus 2 times g is e to the z minus g prime is e to the z, and f is 9z to the 4th minus 7z squared plus 2z plus 12 all over g squared. So that's e to the z squared. And that would be that derivative. Oh, we might be running out of a little room here, but I'm sure we can work it out. All right. So for C, we have F, and we have G. And it might be a good time to remind you of the derivative of ln. So the derivative of ln, we'll do ln x, is 1 over x. Right. This gets used down here. So our f is ln t plus 5e to the t minus 12. F prime is 1 over t plus 5e to the t. So we're not going to, with 5e to the t, it just stays 5e to the t. And then the 12 just disappears because the derivative of a constant is 0. For g, we have t to the 4th. And then for the square root of t, I'm going to rewrite that as t to the 1/2 power plus t. And then g prime, we have 4t cubed. This will turn into no, that won't turn into a plus sign. It's not a negative power. This will be minus 1/2 t to the negative 1/2 plus 1. So the derivative of this function using the the quotient rule, I know it has that little blue part that came down with it, but I am not going to fix that. So using that product rule, not product quotient rule, keep on saying product when I mean to say quotient, using that quotient rule, f prime is 1 over t plus 5e to the t. And it's important to put these parentheses here. If you don't have your parentheses, oh wait, why isn't the 12 included? So are you talking about, so somebody just asked, why isn't the 12 included? Are you talking about this guy right here? Oh, wait, hold on. Because I didn't see that there was a T there. That's why. Good call. Because I wrote the F down wrong. So because F was written down wrong, I then didn't take the derivative of F correctly. So you're right. There should be a 12 there. Absolutely. And then let me just fix that. Thank you. So this was a 12t to begin with. So 12t derivative of 12, negative 12t would be negative 12. So there would be a minus 12 times g of t, which is t to the 4th minus t to the 1/2, or you could use the original, you could use this guy as well, it doesn't matter, plus t, minus g prime is 4t cubed minus 1/2 t to the negative 1/2 plus 1 times f is ln t plus 5e to the t minus 12t all over, dun, 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 dun. Oops, oh, wait, whoa. When I say it's been a long day, would you believe me? It's been a long weekend, guys. Here's the problem, guys. This isn't a quotient because this isn't a quotient. This isn't a fraction. So this isn't a quotient. This is a product rule. Oh, goodness. This is a product rule. One of those weekends. Did inevitably get my tenure binder then, though. It's a product rule, so let me just point out what happens here. I use the quotient rule, but this isn't a quotient. This is two things multiplied, not being divided. This should be product rule, which, see, the nice thing about doing product rule the way that I do it is that fixing something that should be a quotient rule or should be a product rule into a quotient rule or vice versa becomes really easy because then you just change the sign in the middle. Bam, got it all fixed. So the entire thing becomes fixed and there's no problems at all. Bam. So once again, two things being multiplied is product rule. Two things being divided is quotient rule. All right, let's hope we can fit this in here. I'm hopeful. So top part is F. This will be quotient rule because it is two things being divided. This is G. So for F, I'm going to rewrite this as exponent fractions. So we have raised to the 4/3. This one already has its exponent, minus 20 ln y. And for that derivative, that's going to be 4/3. If you bring the negative 4/3 y to the 1/3. If you bring the negative 1 down in front, it'll multiply with that negative, and it's going to be plus y to the negative 2, because you're subtracting 1 on the exponent, minus 20, and then the derivative of ln y is 1 over y. G is y to the 5/4 plus 3y to the negative 1/2. G prime, 5/4 y to the 1/4. Negative 1/2 times 3 is minus 3/2. Y to the negative 3/2, because you're subtracting 1 from negative 1/2. And then what can we do here to make room? Well, I can erase. Yeah, that should be enough room. Haha. I know it's kind of cheating, but yay for technology. H prime of y here, because we are dividing two things, we are using quotient rule. This time for real, because we are dividing two things. So f prime, 4/3 y to the 1/3 plus y to the negative 2 minus 20 times 1 over y. That's f prime. Times g is y to the 5/4 plus 3y to the negative 1/2 minus g prime is 5/4 y to the 1/4. Oops, no closing yet, right? Don't close your parentheses yet. Minus 3/2 y to the negative 3/2 times f, which is y to the 4/3 minus y to the negative 1 minus 20 ln y. That's going to fit in there just barely. Over g squared. So y to the 5/4 plus 3y to the negative 1/2, and then square it. So what I can tell you is that normally in a regular semester, first of all, I don't give you these formulas on the test. This is something you have to have memorized. This is very common in calculus courses. Most calculus courses will not give you the formula for product or quotient rule on an exam. So it's something you have to have memorized. Since you're allowed to use your notes for these exams, even in a classroom normally, when you're not allowed notes and you don't have these formulas, I still mark down if you get the formula wrong, because it's that important of a formula. In these tests, when we come to test number 2, exam 2, I'm really not going to be forgiving if you use the wrong formula, because you have it right in front of you. You have opportunities to double check, triple check your work. You have a lot of time to do it. So please make sure that you are using the correct formula. Making a mistake like I was making here, make sure you're double checking your work to see, oh, is this actually product rule? Should I have been using product rule here? Make sure you're using the right rules and make sure that you have them written down correctly. Can I answer any questions on these practice problems? Hopefully that helped a little bit so that you were able to practice. So you get to the point, and my hope is that you'll get to the point where you're not writing this part down anymore. You're actually just going straight from this to this. That's the point you're going to get to. I don't suggest going there at first. I do suggest writing these down so that you can just kind of easily place them where they need to go. But you do want to eventually get yourself to the point where you're just going straight for that answer. No questions at all? No concerns, comments? Okay. So let's go ahead and let's try something here. So this first one, you have enough to do this first one. Go ahead and try this first one out. I'll go ahead and stop the recording for a sec. Forgot to start recording. Sorry, people who are watching the recording. I was just talking about fraction math up here. I was just talking about how if you're subtracting 1 from a fraction, that you are essentially just subtracting the denominator from the numerator and leaving the denominator alone. So if you have 5/7 minus 1, 5 minus 7 is negative 2, and then over 7, and 19 fifths minus 1, 19 minus 5 is 14 over 5. So that's what you missed on the recording before I pushed record. Now we're going over here to finishing this derivative. The derivative of negative 5 is 0, so nothing there. G is 9 ln x plus x. The derivative of ln x is 1 over x, and the derivative of x is 1. So t prime of x is, let me write down the formula, f prime g, then let me center this better. There we go. F prime g, this is a product, right, because it's being multiplied. So product rule plus g prime f. Now, one way to help you kind of remember this one is that the quotient rule is for when you're dividing two things, and the quotient rule has division in it. So the way that I like to think about it, like the division belongs with the division. If you have division, then you're using the one that has the division. If you're multiplying so you don't have a division, then you're using just the one that's one line, no denominator. Anyways, f prime, 3/4 x to the negative 1/4 times g, 9 ln x plus x, plus g prime, so 9 times 1 over x plus 1, times f, x to the 3/4 minus 5. And there is my derivative. Questions, comments, concerns on that one? So moving on to B, there's a reason that I wanted to save B for us working together. And that's because of this tricky little thing that happens right here. So f is equal to t cubed e to the t. This is actually two things being multiplied together. This is actually a product rule moment. This requires product rule to take the derivative of just the numerator. This overall function is going to require quotient rule, but the numerator requires product rule. So we're going to get kind of abusive with our notation, but I'm going to call this guy F and this guy G. And I know it kind of makes no sense because this is F and this is F, but you know, I think it's just easiest if we stay with F's and G's here. So F is t cubed. F prime would be 3t squared. Oops, that's a t. It says tt squared. 3t squared. G is e to the t. G prime is e to the t. So the derivative of f would be f prime g plus g prime f I'm going to now write it all in the same color. I'm going to write it all in purple. But I am using f prime g plus g prime f. So we have, I don't need to do parentheses on this one, f prime g, because there's nothing being added or subtracted here, so I could just leave the parentheses off. Plus g prime f, so e to the t, t cubed, which we would normally write t cubed e to the t. Right, so once again, this is f right here. This is f prime. G is this bottom function, t plus 1. G prime is just going to be 1. This big function was a quotient of two functions, so we are using quotient rule here. Right? F prime g minus g prime f all over g squared. It's all kind of cramped in there. There we go, put the g squared right there. So f prime, that's this guy down here, 3t squared e to the t plus, I'm going to write it as t cubed e to the t because that's just the more natural way to write this part right here, times g, which is t plus 1, minus g prime is 1, and f is t cubed e to the t, all over g squared. So t plus 1 quantity squared. Now you are, of course, allowed to simplify these if you'd like. Some of the answers in the answer key for section 2 do have them simplified, but you do need to show all your steps. So you could simplify this and write a simplified answer, but you do need to at least show this step exists, that you got this step, and then simplify from there. You can't go just straight to a simplified answer. So do make sure that you're writing all your steps down on the homework on exams as well. Any questions on these? Right. All right. So we have another one. This is going to be a longer one. All right? This is going to be a longer one. So, overall, we have two functions being multiplied, right? Right here. We have two functions being multiplied. So, what we should have for k prime of t, because the big picture is that two things are multiplied, we should have product rule, right? We should have f prime g plus g prime f, where this is f. My apologies. Let me mute myself. Sorry about that. All right. Sorry about that. My dogs. I think we got a package. So they went a little bit nuts there. All right. And this guy is G. So that's the big picture here, is that we have to take those derivatives. Now, much like the other problem we did, one of these functions we need to use quotient rule on. You might think we need to use quotient rule here, but we don't, and I'll talk about that in a second. But I'm going to take this guy. My f function is t cubed plus 3t plus 2 over t squared minus 1. And then I'm going to call, let's use pink for some of this. I'm going to call this top one f. I know we're abusing notation here, but we have to do quotient rule here. So I'll call this guy f. And I'm going to call this bottom guy g. And we're going to do quotient rule on him, and maybe I'll put a space for where we will have our answer, but I'm going to come over here and write the formula down. So we have f prime g minus g prime f over g squared, using these guys right up here. So to get the derivative of this guy, of f, we need to take quotient rule for this one. So we're taking like mini derivatives here. So the derivative of this new f, again, we're being abusive with our notation, but it's okay. We know what we mean. So we have the derivative 3t squared plus 3. For g prime, we have 2t. So this derivative, f prime, is 3t squared plus 3. G is t squared minus 1 minus g prime is 2t. F is t cubed plus 3t plus 2. Just let me do that in purple. All over g squared. So that's t squared minus 1 squared. So I'm going to rewrite that here, but I'm going to write it in purple so that it's all the same color. So we have 3t squared plus 3 times t squared minus 1 minus, Oh, we're going to run out of room. Move it over a little. I'll just move it up here. All right. Minus 2t times t cubed plus 3t plus 2 all over t squared minus 1 quantity squared. So that's my f prime. Now time to take the derivative of g. And by g, I mean this g up here. And you might think to yourself that we need to use quotient rule on this guy, and that's something I see people do on tests a lot, and it's really unnecessary. You do not need to use quotient rule on this. Right? So 3 over t squared is the same thing as 3t to the, oh, this is going to run into the q, as 3t to the negative 2. So really what g is actually 3t to the negative 2 minus t8 to the 5th, and we can use power rule. So I can just erase him. Well, I guess I'll just leave him. But we're using this guy for g. And then g prime would be negative 6 t to the negative 3 minus, bring the 8/5 down. And then for the exponent, 8 minus 5 is 3, so we have 3/5. So we have g and g prime. We have f and f prime. Our original used product rule. Are we going to have enough room? Hard to say. All right, so f prime, this guy right here, big parenthesis, 3t squared plus 3 times t squared minus 1 minus 2t times, I'm literally just copying it down, t cubed plus 3t plus 2 all over t squared minus 1 squared. So that's f prime. G is right here, or you could use this one. It doesn't matter which of these versions you use. They're both the same. Just parenthesis. I'll just do 3t to the negative 2 minus t8 to the 8/5 plus g prime, this guy down here, negative 6t to the negative 3 minus 8/5 t to the 3/5 times f, which right up here, the original f, t cubed plus 3t plus 2 all over t squared minus 1. And bam, you got yourself a derivative. So, longer problem, but can I answer any questions? And by the way, this got put right down there. So for this next one, I'm actually going to leave this one for you to do on your own, but I'm going to give you a hint on it. The hint on it that I'm going to give you is that this first guy can be f and make this entire next part g. So my suggestion, I want you to do it on your own and we'll talk about it when we come back to class because I want to get to the next page. My suggestion is doing 3x squared plus 5x minus 2 for your f, and then for your g, you have 1 plus square root x times x to the negative 3 plus 7, and then you'll have to use product rule on him to get his derivative. So we'll go over the answer next time in class, but try that one out on your own. You'll use product rule on that second part. All right. All right, so some new notations. If you see a long line after a derivative, in particular, you don't really see this as much as you see this. dy dx, there's a long line and x equals a at the bottom. This just means the derivative evaluated at x equals a. i.e., plug x equals a, plug a into the derivative. So we use that notation sometimes. Really, this guy right here, it's like the same thing as saying f prime of a, because you're plugging a into the derivative. So we're going to do some graph problems here. We're given a graph. We're given some information about the graph f. So this is f. We have some information about g and g prime. We don't know what it looks like. All we know is this information. And we're asked to find the derivative of the quotient of f and g evaluated at 1. So we're going to need to find this derivative. Keeping in mind this right here is just quotient rule. So that's f prime g minus g prime f over g squared. But then we add in this component of evaluating it at 1. So evaluating it at 1, we'd have f prime of 1 times g of 1 minus g prime of 1 f of 1 all over g of 1 squared. So all I did from here to here, so I know this is quotient rule, so I wrote down quotient rule. And then it said evaluated at x equals 1, so I just took each of the functions, right? 1, 2, 3, 4, 5. I took all 5 of those and I'm going to plug 1 into it. And some of these are going to come from the table, and the others are going to come from the graph. So from the table, right, we can get g of 1, right? G of 1 is 2 from the table. And g prime of 1 we can also get from the table. Right, so there's this. G prime of 1 is 6. And then once again, we already got g of 1. That was 2. We already found that. So the things that we have left to find are going to be f prime of 1 and f of 1. So f of 1 is just the y value at x equals 1 on the graph. Right, so here's 1. Looks like this y value is -3. For the f prime of 1, f prime of 1 means the slope of the tangent line at x equals 1. So the tangent line, if you're kind of looking at this, at 1, so tangent line like right here would be like this, right here it would be like this, but down here at the bottom of a hill, it's just going to be flat. That tangent line is just going to look like this. It would be a horizontal tangent line. When x is equal to 1. That means that f prime, if the tangent line has a horizontal slope, that means f prime is 0 because the derivative, the slope of the tangent line is 0 at x equals 1. So if I come back here, f prime 1 times g of 1 minus g prime 1 f of 1 all over g of 1 squared. We now have all those values, right? We have all those values to plug in. So f prime of 1 is 0. G of 1 was 2. Just getting that from here. Minus g prime of 1, we said was 6. F of 1, we said was -3. All over g of 1 squared, and we said that g of 1 was 2. So we can just simplify. We have 0 plus 18 all over 4. Simplifies down to 9/2. So 9/2 would be that value. Now, I want to come back, I think, to this one because I want to make sure we get to the next page and we have 10 minutes left. So I think what I'll do is I will come back on Wednesday for this one, just so that we can get to the next material. If we have time on Wednesday, we'll come back to it. If not, it's not the end of the world. In the meantime, I am going to move on to the next page so that we can talk about some trigonometry real quick. All right. So trigonometry is pretty cool. We're going to talk about some derivatives of trig functions, and we're going to start with some nice basic trig functions, the ones we like the most, sine and cosine. And their derivatives are pretty fun. So the derivative of sine is cosine. And the derivative of cosine is negative sine. All right, so this is important. There's a negative right in front there. So the derivative of cosine is negative sine, and the derivative of sine is positive cosine. This will get really confusing later in the semester when we reverse it, when we go to talk about integrals, but don't worry, I'll bring it up again then about how it gets confusing. So we're now going to use the rules that we have in these two derivatives to derive the rest of the trig and derivatives. So leave a blank spot here because we're going to put in the actual derivative of tangent once we've simplified it. But for now, tangent. Tangent is equal to sine over cosine. So we're trying to take the derivative of tangent, and we have sine over cosine. So we can assign a sine f and g and do quotient rule here. So f is sine, and the derivative, I'll put parentheses there for good measure, the derivative of sine is cosine. For g, we have cosine, and the derivative of cosine is negative sine. So using our quotient rule, because this is a quotient, f prime g minus g prime f all over g squared. F prime is cosine x. Now I'm not going to put parentheses on these because these are all just one term things. Well, I will put parentheses on, him because he has a negative. Can't even point. There we go. So f prime is cosine x. G is cosine x minus g prime is negative sine x, and f is sine x over g squared, which is cosine of x quantity squared. This simplifies down though. So for instance, cosine x times cosine x is actually cosine squared x. And then this negative and this negative become a positive, and then sine times sine, well, that's going to be sine squared x over cosine squared x. Now you might be tempted to do maybe some canceling, but you can't really cancel these, right? You can't really cancel these because sine squared x doesn't have a cosine squared x in them. But do we know something about cosine squared plus sine squared? Anybody want to mention sine squared plus cosine squared? Hopefully drilled into you in trigonometry excessively. Hopefully used a lot. Sine squared plus cosine squared, anybody? 1, there it is. 1. It's 1. So you have 1 over cosine squared x. And 1 over cosine squared is just secant squared x. Right? We're deriving it now so you don't have to ever derive it again. The derivative of tangent is secant squared x. Right? The derivative of tangent is secant squared x. So you don't have to derive this again. If you see tangent, you now want to think derivative is secant squared. For cotangent, this becomes really similar process. In fact, it's so similar that I'm going to kind of go through it a little faster, especially because we only have 4 minutes left. But really, cotangent is cosine over sine. So we're going to do that same process of quotient rule, but we're going to do it with cosine as the f function and sine as the g function. So really being fast about this, f is cosine x. I'm not going to color code. F prime is negative sine x. G is sine x. And g prime is negative sine x. Not negative sine x. Woof. Cosine x. Positive cosine x. Just started looking at the next slide over. Positive cosine x. So it's f prime g, so negative sine x times sine x, minus g prime, so cosine x, f cosine x, over g squared, so sine squared x. On top, you have negative sine squared x minus cosine squared x over sine squared x. You can factor out a negative on the top, so you have positive sine squared x plus cosine squared x all over sine squared x. Once again, sine squared plus cosine squared is 1, so you have negative 1 over sine squared x. And that's the same as negative cosecant squared x. So the derivative of cotangent is negative cosecant squared x. Once again, you don't have to derive those again. You now have those. So we only have 1 minute left, which is not enough time for us to do the other derivatives. So we are going to, I guess, finish this up on Wednesday. Yeah, I guess we'll have to finish that up on Wednesday. If you have questions, I will stick around and answer them. Otherwise, I hope you have a fantastic Monday. I will be grading those exams soon, probably not today, but hopefully I will start tomorrow. Thanks for being here with us and have a good day.